So for our presentation, we're going to be focusing on ICON Interactive Conversational Memory Network for Multimodal Emotion Detection. So the motivation for this paper and research basically is emotion recognition being a multidisciplinary field, stemming research from psychology, cognitive science, and machine learning. And all of these are just designed at improving human-computer interactions, which are increasing at a rapid pace with things like smart assistants, automated calls, and many others. And all of them are just designed at improving these interactions by allowing the computer to recognize the emotions of the human part and be able to better respond to it. So one of the main things that this paper is focusing on is including self-dependencies and interpersonal dependencies. So most of the research before was just focused on self-dependencies, which is really monologue-based emotion recognition, whereas now ICON is also including interpersonal dependencies, so how the other person affects our emotions and how we express them. So more so getting into conversational emotion recognition, along with a lot of other parts and features that they are using. But basically, this is interpersonal dependencies. An example, you can see person A starts out just frustrated, and person B is responding neutrally and almost sarcastically without any empathy. And you can see by the end that this is affecting person A, and they become angry. So this is just a great example of those interpersonal dependencies.
For feature extraction, CNN is used on text data and visual data and passed through dense layer whose activation values are taken as respective features. OpenSmile is used on audio data to extract features, and L2 feature selection is performed to get a low dimensional audio features. Gated recurrent unit is similar to LSTM, which uses the current input and the previous state, also known as hidden state, as inputs. It calculates two gates, reset gate and update gate, which decides how much of the previous state has to be erased or updated. Here we can see sigmoid activation is used to calculate a reset gate and a update gate, which are multiplied with the hidden state to find the final output and the next hidden state. Self-influence module calculates the emotion inertia for individual speakers. It performs a GRU on the features extracted and the personal history of the speaker. Dynamic global influence, it calculates the conversational emotional inertia. It performs GRU on the information taken from the SIM and the previous conversational history. Multiple memory read and write operations are performed. In memory read, weighted memory vector is calculated and multiplied with the test reference, which is passed through the prediction phase. For the memory write, all the memory cells are passed to a GRU to calculate the next memory cell and save and pass to the next hop. Here we can see the for each individual users the utterance, the audio and video files are extracted, the features are extracted, performed on a GRU, which uses only the personal history, and passed to DGIM, which uses the conversational history and written in the memory. A test utterance is given and multiplied with the weighted average, a weighted memory weighted representation to give it to the prediction phase, which is a softmax activation. All the memory cells are taken to a GRU to calculate the next memory cell and pass it to the next hop.
In this section, we'll have a look at the experimentation part of the paper. The network is fed data from two main sources: the interactive emotional dyadic motion capture dataset and the sustained emotionally colored machine-human interaction using non-verbal expression datasets. For simplicity's sake, we'll be using their acronyms. EmoCap is a database consisting of videos of conversations between pairs of 10 speakers, where each pair is assigned a diverse scenario of dialogues. These videos are segmented into utterances with annotations of fine-grained emotion categories. 6 such categories have been considered for the classification task: anger, happiness, sadness, a neutral state, excitement, and frustration. Semaine is a video database of human-agent interactions where users interact with characters whose responses are based on the user's emotional state. For the purposes of this paper, the authors utilized AVEC 2012's fully continuous sub-challenge that requires predictions of 4 continuous affective dimensions, which are arousal, expectancy, power, and valence. Now let's take a look at the training details. The extracted data is divided into a train test split in a ratio of 80 to 20, with a further 20% of the training set being set aside as a validation set for hyperparameter tuning. The model is then trained using the ADAM optimizer, which is an adaptive learning rate optimization algorithm. The author started with an initial learning rate of 0.001, and this is carried out for 10 epochs. The network is also subjected to dropout and gradient clipping for regularization, and finally, the best hyperparameters are decided using a grid search. After training and testing, the authors compare their work with multiple state-of-the-art networks in multimodal utterance level emotion detection, and these results will be taken up in the next part.
So we can start first looking at the results from the EmoCap dataset. And here in this table, we have a column for each of the emotions that are being classified. And for each of the emotions, we have an accuracy metric as well as an F-score metric. And we are tracking the results for each of the baseline models as well as for the icon model. In each column, the best score is bolded, so we can look very quickly and see that the icon model is outperforming the baselines for the sad emotion, neutral emotion, excited emotion, and frustrated. For the angry emotion, it's outperforming in the F-score, but there are some models outperforming in accuracy. And for the happy emotion, it's doing okay, but again, there are models outperforming in both metrics. Looking at the average score, we can see that the icon model is outperforming as a whole in both accuracy and F1 score. So these are pretty impressive results. Moving on to the results for the CMAIN dataset, we have a very similar table here. And again, the icon model is outperforming the other models in all metrics. In some cases, there are other models doing as well as the icon model, but it is always doing at least as well as the baselines, if not better. And the final result to look at is a comparison of how the different data modalities affect the performance of the model. So here the model is used using only text data, only audio data, only video data, and then the various combinations of the data. We can see that there is the highest performance across all metrics when all three of the different types of data are being used. But we can also find that there's not very much a difference between using all three sources of data and using just text and audio and leaving out the video data. We see a reduction in accuracy of only 0.2%, which is not very significant considering that you're entirely leaving out video data, which can be quite a lot of work to work with, and you can obtain nearly the same result without using it.
So now we're going to look at related works that were cited in this paper, and then we're going to look at how all of this ties into our project at the end of the day. So when these researchers were looking at prior art, they looked at three different main categories. They looked at data processing, so things like feature engineering, and then they also looked at human language, so psychology papers, and that gives us context as to why we're going to be classifying things in a certain way, and gives us clarity as to why we're making these decisions. And then they also looked at architectures, in particular memory networks, which is just a particular, very similar to recurrent neural networks. So this is one of the papers that they looked at. It's very important, very similar to what they were doing. It looks at facial structure and it looks at audio, and it looks at how those both change over time, and it gives a lot of clarity and insight into what to expect when it comes to analyzing these kinds of emotional trends over time. And next, there's another paper that was also very important. So instead of using standard recurrent neural networks, they looked at these things called memory networks. And basically what they do is, as you see up here with this little equation, it has M, which is a memory array, a memory database. And we assign the input, so we parse the input and then make it into an input feature mapping. So a bunch of features are then inserted into M at a certain place defined by H. And what this does is it compartmentalizes this data, and it's very different than long short-term memory and other kind of techniques where things are forgotten. There's a forget gate. This is very important because it keeps and retains this information. And you see with this little blurb right here, it was able to remember certain facts about the statements that were said before. So how does this apply to our project at the end of the day? All this stuff. So it's mostly about knowing what to expect. When we're dealing with complicated memory-based learning and this kind of stuff with emotions, it's important to understand how these trends are going to change over time and what kinds of architectures are needed in order to deal with those changes. So in this paper, they use GRUs, which is basically very similar to LSTM, but without an output gate. It's actually more efficient to use GRUs. But this is something we should definitely take into consideration and perhaps use alongside LSTM and test to see which one's better. Also, this paper does a great job with model interpretability and visualizing justifications for why they draw various conclusions on input data. And that's something we should work on as well.